Welcome to this explainer. Have you ever looked at a massive robotic arm, an aircraft flight controller, or an industrial power grid and wondered exactly how engineers predict its behavior without drowning in pages of complex differential equations? Well, you are in the right place. Today, we're unpacking the fundamental challenge of control systems engineering, analyzing system dynamics. We're going to explore how a truly elegant graphical tool saves us from overwhelming algebra, allowing us to literally see the stability and performance of a system.
Here's our roadmap for today. We'll start with an introduction to frequency response, move into the power of logarithms, break down the anatomy of poles and zeros, construct a composite plot, analyze system stability, and wrap up with margins and real-world design. Let's break down these complex mathematical formulas into intuitive, visual frequency domain responses.
All right, Part 1. Introduction to frequency response. Moving from time to frequency.
So before we start drawing lines, what are we actually measuring here? We're looking at the frequency response. Simply put, it's the steady-state response of a stable system when you feed it a sinusoidal input signal at various frequencies. Think about testing a high-end audio amp, or maybe an industrial DC motor control system. You send in a sweeping sine wave, starting low and ramping up high, and you just measure how the system reacts at those different speeds. Does the motor track the signal perfectly? Does the amp boost the bass but completely muffle the treble? That reaction across the spectrum, that is your frequency response.
And this is exactly the problem we're trying to solve. If you stay in the time domain to predict how that motor or amplifier behaves, you're stuck solving brutal, complex, high-order differential equations. It's mathematically exhausting. But if we shift over to the frequency domain, we completely bypass that heavy lifting. Those nightmare differential equations turn into much simpler algebraic ones, which we can literally just plot out on a graph.
Moving on to Section 2, the power of logarithms. H.W. Bode's graphical genius.
We have Hendrik W. Bode from Bell Labs to thank for this massive paradigm shift. He realized early on that engineering systems deal with enormous ranges of frequencies and amplitudes. If you try to plot that on a standard linear scale, it's useless. The low frequencies get completely squished together, and the high ones fly right off the page. The fix? Logarithms. We use the decibel, or dB, which is calculated as 20 times the base 10 logarithm of the transfer function's magnitude. Using decibels alongside a logarithmic frequency scale completely revolutionizes how we compress and visualize huge spectrums of data into neat, readable charts.
There's this fantastic quote from the source material that really hits the nail on the head. The primary advantage of the logarithmic plot is the conversion of multiplicative factors into additive factors. This is the absolute genius of Bode plots. In the frequency domain, a transfer function is made up many factors multiplied together. But thanks to the magic of logarithms, we don't have to agonize over multiplying complex polynomials. We get to just add simple, straight lines together.
Section 3. Anatomy of poles and zeros. The building blocks of the plot.
Okay, so to add those lines together, we first need to know what they're made of. Any complex transfer function boils down to specific building blocks: constants, poles, and zeros. A constant gain just shifts your whole graph up or down with a zero slope. A simple pole starting at its specific break frequency gives you a downward slope. And a simple zero, that gives you an upward slope. Every single factor contributes a totally predictable geometric slant to our plot.
And here is the magic number to remember. -20. -20 decibels per decade. That's the exact downward slope contribution of a simple first-order pole. If you have a basic RC filter circuit in power electronics, once you hit its break frequency, the signal's magnitude will reliably roll off a -20 dB for every decade, or factor of 10, increase in frequency.
Of course, not every system is that simple. While a first-order system maxes out at that -20 dB per decade slope, second-order systems are a different beast. They introduce complex conjugate poles. Picture a physical mass and spring system, or the stabilizing rotors on a drone. These introduce a resonant frequency peak, which is a huge spike in the system's response, followed by a much steeper drop-off, bringing a -40 dB per decade slope to the party.
Part 4. Constructing the composite plot, putting the pieces together.
Now for the fun part. We take those building blocks, our gains, our +20 and -40 slopes, and we synthesize them. Sure, today everyone uses software like MATLAB or Simulink, but sketching a Bode plot by hand is absolutely essential for building your engineering intuition. It really just takes 3 steps. First, identify the corner, or break frequencies for all your poles and zeros. Second,
draw the straight-line asymptotic approximations for each factor. And third, add a slight, smooth correction, usually about 3 decibels, right at those break frequencies to get your actual real-world curve.
Watch how these geometric slopes stack up as we sweep across the frequency spectrum. From 0.1 to 1 radian per second, a pull at the origin gives us a -20 slope. But right at 1 radian per second, boom, a new pole activates. We just add its -20 slope to our current one, giving us -40. At 2 radians per second, a third pole kicks in, dropping our total slope down to -60. It shows exactly how mapping a complex system response is literally just sequential graphical addition.
Section 5. Analyzing System Stability, the climax of the Bode plot. Now, drawing the lines is just the setup. Figuring out if the system is going to stabilize or spiral dangerously out of control is why engineers actually use this tool. When we look at the phase plot, which is the second half of our Bode diagram, we are hunting for one absolute critical threshold, -180 degrees. If your system's phase shift hits -180 while the gain is still high, the feedback that's supposed to correct errors will actually amplify them. That leads to catastrophic instability.
So how do we know we're safe from that critical point? We look at 2 metrics, gain margin and phase margin. Gain margin is the change in open-loop gain required right at that -180 degree mark to make the system unstable. Phase margin is the change in phase shift needed at unity gain, which is 0 decibels on the magnitude plot, to cause instability. Visually, on a Bode plot, these are literally just the vertical distances between your curves and those critical danger zones.
And this brings us to a pretty binary outcome in control design. A stable system will show a positive gain margin in decibels and a positive phase margin in degrees. A positive margin on the plot is literally your safety buffer. It tells you how much wiggle room you have before things fail. Conversely, if those margins are negative, your system is unstable and you've got to redesign it.
Finally, Section 6. Margins and Real-World Design, Compensators and Performance.
Let's see how engineers use this visual safety data to build better systems in the real world. From a finished Bode plot, we extract key performance parameters: gain margin, phase margin, system bandwidth, and the resonant frequency peak. These aren't just abstract academic numbers, they dictate physical reality. Your phase margin controls the transient response, basically how much the system overshoots. Your bandwidth dictates speed. A wider bandwidth means a faster reacting system, which is absolutely crucial for things like electric vehicle control systems or automation.
Now, what if your system is underperforming? We fix it by adding mathematical controllers called compensators to reshape the Bode plot. Take a disk drive read system, for example. An uncompensated drive has a low phase margin and a narrow bandwidth, meaning it's sluggish and prone to crashing. But if an engineer adds a lead compensator, it physically alters the transfer function. Visually, on our plot, the bandwidth widens for a faster response, and the phase curve pushes up, creating a much safer, more stable phase margin.
Which brings us to a final thought. We've seen how sketching out these lines reveals the hidden dynamics of incredibly complex machines. But if a system's phase margin visually tells us exactly how close it is to instability, how can we use Bode plots to automate the design of controllers that perfectly balance rapid response with absolute safety? The graphical foundational skills we've covered today are the exact same principles powering the algorithms inside modern automated control design software. Thanks for joining me for this explainer, and keep questioning how we visualize the unseen forces of engineering.